All right, so you guys should have written in your composition books, Lab, this is Lab P.8.5 Energy Transfer and Power. So today, the whole goal of this lab is to be able to determine who is most powerful when going up a flight of stairs. To begin though, I want to start with the pre-lab. And so, if you look down at the pre-lab questions, number 1, it says to draw an LOL chart for a box that is raised from ground level to a height that is greater than 0. Include the box and the earth as a system. And it took 2 seconds to do that. So, on question number 1, I'm going to draw an LOL chart. L-O-L. And in my system, it told me to define as the earth and the box. And really, I don't need to define anything else, because that's the only thing that's really changing about this. And so, both at point A and at point B, it's motionless. And so it'd be like, if I started it off at the ground, picked it up, it's motionless. Now, I had to put it in motion to get there, but we're just focusing at the very end result. And so, motionless, motionless. Therefore, there is no kinetic energy. The only kind of energy that there might be at this point, gravitational, but it's at ground level, so therefore we're defining that as 0. And so then after, the gravitational should go up because I'm increasing my height. And so I'm like that, perhaps. Well, where'd those 3 bars of energy come from? Well, they had to be put in from the outside of the system. 3 bars going in. And so therefore my equation in this case, remember anything that's entering or leaving the system we define as work being done on the system. And so this is work. So my equation would be work is equal to the gravitational energy. And then it did also tell me on that problem that it took 2 seconds to go from point A to point B. And so in green over here, I'm just going to write parentheses 2 seconds to represent that that was done in 2 seconds. Okay, then number 2 says, do the exact same problem. You're taking the same box, same mass, everything, and you're lifting it up to point B, but the only difference is that the height stays the same. The only difference between these guys is that it takes 10 seconds to do that. So how is that going to affect my LOL chart? I look here and I'm like, well, where is time in there? It's not. It's not in there. And so maybe you might be thinking, well, should I be doing, maybe it's going to have less gravitational as with it, so I'll show 2 bars. But you can't do that because it's going to the exact same height. So therefore, it's got to have 3 bars going in. Well, wait a minute. If that's that, and I still have no gravitational, then what's the difference? Absolutely nothing. There's still the same amount of work done. It just takes longer to do. E gravitational, same exact equation, except now it's done in 10 seconds. And so then number 3 asks the question, well, what's the difference between these LOL charts? And the answer is nothing. Nada. But then number 4 says, well, what is different about these guys? So the only difference is that this physical scenario of me lifting a box from A to B in 10 seconds, this is going to take longer than lifting it in 2 seconds. That's simply the only difference. Still same amount of work being done, same amount of energy transferred, but it's just done for a longer period of time. So now 5 is kind of tying this to what we're talking about today. And so now instead of talking about a box being lifted, we're going to do a scenario in which we are going upstairs. So I've got a staircase here and a person who's walking up them. Okay? At the beginning part, he has no velocity. At the top, he does have some velocity, so it's greater than 0. His height here is greater than 0. Here, his height is equal to 0. And it tells us on this problem, this is really important. This is question number 5. This is really important because when we define our LOL chart in our system, we're defining the system as the person because we want to make sure that we're accounting for the person's moving energy, kinetic energy. And so the person is in there. And the earth is also in there because we need to make sure that the gravitational energy is there. But what's not in there is his muscles or the chemical energy that's allowing him to go up there. We want to consider that outside of our system. So we are calling EK, EG, EK, EG. At the beginning, he has no height and he has no velocity. Therefore, X, X, nothing. Afterwards, he has both height and velocity. And so I have to show some kind of bars here. It doesn't matter how many bars, it doesn't matter the distribution. You're going to see in this lab, you're going to quantify how much of each one and be able to see how they compare. That's that. And so in order to make this work, I've got to have 2 bars going in. And so therefore, my equation in this case would be work is equal to the kinetic energy, EK, plus EG. And so that is number 6 for the energy transfer. This part is huge because this is going to help us answer the question down in the analysis. Like for instance, this is really important because some people in Blue Day kind of struggle with this. For instance, if you scroll down to the analysis asks the question, how much total energy was added to the system in order for you to be able to get up the stairs and have some velocity? Well, how much total work had to be added to the system? Well, look, that's work. Work is equal to the kinetic energy plus the gravitational energy. So, if you can determine your kinetic energy, you can determine your gravitational energy, you add them together, that's how much total energy you inputted into the system. That came from your muscles, and which came from your food, and et cetera, et cetera. So, this lab, one thing I will say, the key thing, I mean, once you do all of this, pre-lab stuff, what I want you to do is scroll back up to the background, because the background is really important because it defines what we're trying to look at. Excuse me. If you remember the original box being lifted in 2 seconds and 10 seconds, the only difference between them, the amount of work was the same, the only difference was the time. And that's what we talk about in terms of power, which is the rate at which energy is transferred per unit of time. And I give you the equation and the units, which is watts and things like that. So if you guys have any, you guys should have enough information to be able to do this lab. One more thing that I want to show you. I'm going to grab the iPad out of here, so sorry for the bumpiness. Tomorrow you will need to get your weight. And I know that's kind of intimidating because who likes to look at their weight and who wants other people to know their weight? Well, one thing I will say is this is the force plate and it's connected to the vernier probe, and so I'm kind of getting a way to lie about my weight. You guys don't need to know about that. Anyways, it's connected to the vernier probe. You'll want to make sure that you zero it, okay? And the way that you zero it is, like, it's pretty close to 0-ish. There, it's pretty close. To get it to 0, all you do is tap here and hit 0, and that's it. And it'll get pretty close to 0. So then, when I step on here, all I have to do is look at it, and of course it's being weird. There is my weight, although I kind of lied and manipulated, so don't believe that my weight is actually 807 newtons. That's a lie. Anyways, that'll be your weight. Everyone needs to get their own weight. If you guys have any questions, please feel free to email me.